Hello everyone, I'm Mr. McBrien. This is SPH3U, Nuclear Energy. The Ontario curriculum states that we should be able to solve problems using the mass-energy equivalence equation, that we'll be able to compare nuclear fission and nuclear fusion, and that we'll be able to compare and contrast the characteristics of alpha particles, beta particles, and gamma rays. We're also going to discuss half-life today. So we're going to talk about matter-energy equivalence, talk about calculating total energy from mass, and processes for getting energy from mass. Okay, so many of us are aware already that all matter is a form of stored energy. If that matter can be converted to energy, the amount of energy that can be released is equal to perhaps the most famous equation of all, E equals mc squared, where m is the mass and c is the speed of light, 3.0 times 10 to the 8 meters per second. So, assuming that we can find a processor for converting matter to energy, we can take the simple mass of a given object and calculate how much energy is contained within it. Pretty straightforward. We substitute in 52 kilograms times the speed of light squared, and we get a number, 4.8 times 10 to the 18 joules. And of course, once we get into these big numbers, it's often hard to imagine what that means. So a little research, we can find that an efficient home in Canada can expect to pay about between 4 and 6 times 10 to the 9 joules to heat a given home for a year. So what this means is this number is approximately equal to the heat that we would need to, now take your pick, either heat a home for 1 billion years or heat 1 billion homes for 1 year. So either way you look at it, it's a lot of energy. Okay, having said that, it's pretty challenging to convert a 52 kilogram person into energy. And we can often look instead at a phenomenon called mass defect. And the mass defect caused a lot of challenges early on in terms of looking at the atom. So what is the mass defect? Well, the mass defect is the difference in mass between the sum of the mass of the given protons and neutrons and the actual nucleus that we observe. And so it's worth, when we talk about mass defect, it's worth thinking about electrostatics for a second and the fact that like charges repel each other. We know that the nucleus of an atom is composed of protons and neutrons, and so the net charge on that nucleus is in fact positive. And knowing that like charges repel each other, it leads us to wonder, why doesn't the nucleus simply fly apart? We know the electrons have a greater distance, are away from the center of the nucleus. Why doesn't the nucleus explode from electrostatic repulsion? Well, we can consider one of the early puzzles that atomic modelers had to face. Let's talk about a carbon-12 nucleus. Carbon-12 has 6 protons and 6 neutrons, and we know the mass of a proton to a very accurate degree, and the mass of a neutron to a very accurate degree. And we can sum 6 times 1.007276 plus 6 times 1.08665, and we get a total of 12.095646 atomic mass units for a carbon-12 nucleus. And this number we had available to us, but when we measure the mass, it isn't correct. So the actual mass of the carbon-12 nucleus is 11.996709 atomic mass units. We've lost, if we do the subtraction, 0.098937 atomic mass units. And this defect we can think of as the binding energy of the nucleus, the strong nuclear force that holds it together, and the thing that counteracts electrostatic repulsion. And we can put a number to this, of course, because we can take that mass and plug it into our E equals mc squared equation, convert atomic mass units to kilograms, and we get a value of 1.5 times 10 to the negative 11 joules, which seems like a very small number until we think about the fact that in 12 grams of carbon we have 6.02 times 10 to the 23 atoms. And all of a sudden that value, when we think in terms of 12 grams of carbon, the number of joules associated with this is actually very, very high. Okay, so we can detect aspects of that binding energy in other ways. We can look at the energy stored in the nucleus, released in nuclear reactions in radioactive decay. And here's an example here. Carbon-14 undergoing beta-minus decay to become nitrogen-14. And when this decay occurs, it produces a new a couple of particles which have high energy, and the lowering of the mass of nitrogen-14 versus carbon-14, the additional energy comes out in the form of these particles. Now it's interesting to note what's happened here. We've gone from 6 protons to 7 protons, and from 8 neutrons to 7 neutrons. Has a proton been gained and a neutron ejected? No. What's happened is one of the neutrons has lost its negative 1 electron, pushed off an electron, and this has given it a positive charge and turned it into a proton. Okay, and the difference in mass is released in the form of kinetic energy of the released particles. So we're going to deal with each of these kinds of decay in order. We're going to talk about alpha emission, beta emission, and gamma emission. Those aren't the only types of radioactive decay, but they're the most important ones for us to deal with. So in alpha emission, a helium nucleus is emitted from the nucleus of the isotope. So in this case, we have plutonium going to uranium as it ejects an alpha particle. And it's very interesting to look at the given characteristics of an alpha particle. We can relate this, we can describe this as an equation, and this should make it easy for us to discuss what's going on. So, the top left, of course, is our atomic mass. Bottom left is our atomic number, or number of protons. And we can see that when plutonium decays to uranium-236, it loses 4 mass units and it loses 2 protons. Not coincidentally, the helium nucleus that's pushed off, the alpha particle, has a mass of 4 and has 2 protons. In other words, we can do simple arithmetic to get the resulting particle from alpha decay. little bit about nomenclature. The thing that decays, we talk about it as the parent nucleus. The thing into which it decays, we call the daughter nucleus. And of course, we've already talked about the alpha particle. It's good for us to understand those terms. Now, the mass number that we saw here in the atomic number, as we discussed, simple arithmetic can determine these things. Having said that, we haven't really talked about the actual element itself. And because the atomic number changes, the element changes as well. In this case, we go from plutonium to uranium. And we can simply count off on the periodic table to determine what our new isotope will be, what our new element will be. When the element changes in this way, that's called transmutation. So our next kind of decay. In beta emission, either an electron or a positron, which is the antiparticle of the electrons emitted. So we already talked about carbon-14 turning into nitrogen and ejecting an electron. So in this case, notice that the mass number does not change because the electron has a very low mass. So the mass number doesn't change, but the atomic number does. And so carbon turns into nitrogen when it gains a proton. And another example, we can have the positron ejected and the concurrent change. And notice again, the mass does not change, only the number of protons. So the third kind of radioactive decay we talk about comes when we have an unstable daughter nucleus, which is in a high energy state, and it wants to drop to a lower energy state, and it'll do this by emitting gamma radiation, which is really just super high frequency light. So we can see we have the visible spectrum here, ultraviolet, X-rays, and gamma rays are even higher energy. And we can talk about penetrating power and the implications of the energy of these particles. Alpha particles don't have very good penetrating power at all and can be stopped by a simple piece of paper. Beta particles will go through a piece of paper, but aluminum will stop them handily. And gamma rays, you essentially need lead. So now let's discuss the probability that a given isotope will decay. We usually talk about that in terms of an isotope's half-life. So for many different isotopes, we have a very good measurement of the average time it takes a parent to decay. And this is its half-life, the time it takes for 1/2 of a mass of a given isotope to disappear. All isotopes of all elements have a half-life. Every kind of decay has a probability for any given isotope. And if we know it, and we know a time that's elapsed, we can calculate how much we'll have left from an initial sample. And the expression's pretty simple. The amount equals the initial amount times 1/2 to the exponent of the time divided by the half-life. So if we substitute in exactly the half-life for T, we can see that this exponent goes to 1, and we have half of what we had when we started. Now, in a nuclear reactor, we don't want to wait for radioactive decay. We need to find a way to accelerate it. And that isn't really very easy to do, but we can trigger this kind of decay typically by bombarding the nuclei with neutrons. So we hit a given nucleus with a neutron and it breaks apart and produces more neutrons. And it's easy to see that if you do this in the right way, those neutrons can produce more neutrons, and then we have a chain reaction. So the material starts to go faster and faster as more and more neutrons get produced. And as long as we keep this process under control, it can be quite effective. Now, an example of nuclear fission, we can bombard uranium-235 with neutrons, and it will decay to krypton and barium and produce 3 neutrons. Now that's one way to produce power from mass, but there is another way to do it. We can take light elements like hydrogen and turn them into larger ones by fusing them together. So in this example we have 4 hydrogen nuclei and we can form 1 helium nuclei, and because that's lighter, we produce energy at the same time. And obviously, looking at this, we have plenty of hydrogen on the planet, and helium is a pretty innocuous material to produce. We can wonder why we don't use this for nuclear power. Well, the answer is that it's pretty tough to get those protons to go together. So our net reaction of 4 protons to 1 helium nucleus plus 2 positrons is a way to produce power. The problem is that we have to overcome that electrostatic repulsion between the nuclei. So we have to put a lot of energy in, and by a lot I do mean a lot. It requires enormous temperatures and pressures, and typically those can only be produced in the core of a sun, in the core of a star. And of course, on Earth we don't really want to have those kind of conditions. But they are still working on it inside of magnetic fields, trying to produce the conditions that could create fusion and give us a cleaner power source. Okay, so today we talked about matter-energy equivalence, talked about radioactive decay and how to measure it with measure the rate with half-life, talked about fission and fusion. Lots of practice questions today. Please have a look at your textbook and do the listed questions on decay there, and then follow that up with the additional questions shown here. Thank you. Have a great night.